Good morning, my name is Harold Nowak. I have presented an alternative method for the determination of the stopping time and path in Collatz. Here I explain how this method was derived. First, we define Collatz. S of n equals 3 times n plus 1, all divided by 2, for odd n. D of n equals n divided by 2, for even n. Sequence theory. We can start an iterative sequence with the value 0 and track its path for n steps. Say it reaches 1. All we need to know is the starting value, the end value, and the number of steps. Similarly, we start with 1 on the same path, and after n steps it reaches 3. What would you expect the starting number 2 to reach after n steps? Well, the difference between the end for 0 and the end for 1 is 2. You would expect 2 to reach 3 plus 2, that is, it should reach 5. We can write this into an equation with starting value n going for lowercase n steps. N equals n at the nth step minus 0 at the nth step, all divided by all of 1 at the nth step minus 0 at the nth step. We can apply that to a Collatz sequence. Let n equals 5. 5, 8, 4, 2, 1 is the sequence. Let 0 take the same path. 0 ends up at 0.0625. Now let 1 take the same path. 1 ends up at 0.25. Put these final values into the equation and you get the value n equals 5. So the equation works for Collatz. But unfortunately, the step number is not included in the equation, so we do not know how many steps 5 takes to get to 1. Let us include the step number. To do this, we alter Collatz and multiply each step by 2. The operators become S of n equals 3n plus 1 divided by 2, times 2 to the power of the step number lowercase n, and this is equal to 3n plus 2 to the power of lowercase n minus 1. While d of n equals n divided by 2, times 2 to the power of n, and this equals d. So operator s involves change, while operator d is a null operator and involves no change. Now the Collatz conjecture becomes all n goes to 2 to the power of t. We can put this into the parity equation. N equals 2 to the power of t minus 0 at step t, all divided by 1 at step t, minus 0 at step t. Now 0 at step t we can call capital X. Remember, if n goes to 1 in Collatz, then x takes the same path and reaches a certain value at step t. From the value of x we can reconstruct the path taken. This is because we are starting at 0 and the first non-zero value for x in the path can only be a power of 2. To show this, we can start a path. If n is odd, the first step is 3 times 0 plus 2 to the power of 0, and that equals 1. If n is even, the first step maintains the value. When n hits an s step, the value becomes 3 times 0 plus 2 to the power of lowercase n minus 1, which is a power of 2. Now the denominator in the expression is the difference between 1 at t steps minus 0 at t steps. Here 2 to the power of lowercase n minus 1 is removed from both terms, and you are left with 3 times 1 minus 3 times 0 for each s step. If there are ks steps, then you are left with 3 to the power of k. So we have our parity equation. N equals 2 to the power of t minus x, all divided by 3 to the power of k. And this equation describes Collatz. You are assuming that t exists, and if it does not, then no path exists, and x will not start with 1 for odd n or 2 to the power of n minus 1 for even n. But we need a method to check to see if x is real, or what we call valid. To do this, we reconstruct the whole path. This is done by peeling. Divide x by 2 until odd. The number of times you divide by 2 is called a. Subtract 3 to the power of k minus 1 times 2 to the power of a from x and call this x1. Now divide x1 by 2 until odd. Call the number of divisions by 2b. Subtract 3 to the power of k minus 2 times 2 to the power of b from x1 and repeat the process. The number of unknowns is equal to k, and for x to be valid for k, you must end up in dividing by 2 to get 1. Now if x is valid in k, then t is the correct value for n, and the values of a plus 1, b plus 1, etc. are the positions of the s steps in the path to reach 1. And this path has t number of steps, so fill in the other steps with d. Now if x is invalid in k, then t is not the stopping time for n. From the parity equation we know x is positive, so t must be greater than log n plus k times log 3, where logs are to the base 2. If k is the correct value, then t is the first integer value above this expression, and we call this t min. So for any n, we guess a low k. This defines t-min and we work out x. We then check if x is peeling valid in k. If it is, then t is correct for n. If it is not, add 1 to k and continue checking until you reach the correct k. Of course, it is possible that no k can be found which makes x peeling valid in k. But that is the Collatz conjecture. In my next video, I will describe the quick method for checking if x is peeling valid in k. Thank you for listening.